All right, so comparing functions is what our topic was for class today. And when we're comparing functions, there's a few things that we want to look for. So, things you want to look for within functions. The first thing, you want to identify rate of changes, slopes, whatever you want to call them. Rate of changes and slopes of each of your functions. So, if there's multiple functions, you want to figure out all those rate of changes and slopes. Next thing, look for y-intercepts. Then if you're looking at a function graphically, it's a little bit easier, but in in general, then you want to kind of look at any specific points that might be included. Not specific points. Sorry, I'm writing a little faster than talking faster than I can write. Specific points. So especially when you've got a crazy looking function, for instance, if I draw this, some points that might draw your attention, our y-intercept point, and then all these points where our graph seems to change direction, and then as well as when it hits the x-axis, those seem to be pretty important points overall. As well as if you have a picture like this, you want to see how many sections there are. In this case, there's 1, 2, 3, 4 different sections to this graph that we want to kind of keep track of. And then continuing on, something we're going to talk about when we start analyzing some functions, but some things to look for. So here's our first problem. So Mochi, the panda cub, has been measured and weighed each week since she's been born, recorded in this table. Her brother, Kappa, has been recorded on this table. So to compare them, looks like, well, this one is definitely a linear equation. We want to double check to make sure this one's linear. That'll change things if it isn't. So 1 to 5 is 4, from 5 to 9 is 4, 9 to 13 is 4. That's not enough. You have to check both sides. Just because these are all 4s doesn't mean anything. You've got to make sure that they stay consistent. They're all 1s, so we're good. For instance, maybe the 5th week, they have 21. That change of 8 is not enough to go, not linear, doesn't have a constant rate of change. Not enough. Because if you look at the other side, change by 2. 4 over 1 is the same as 8 over 2. So you got to check all the rows, and you got to check both sides. All right. So it is linear. By checking if it's linear, we just figured out the rate of change. 4 over 1. So Mochi is gaining 4 pounds every week. And it looks like here's our y-intercept point. B, Mochi was 1 pound. All right, it doesn't even say, oh yeah, in pounds. So this one doesn't say what the weight is. It could have been in tons for all we know because it's not labeled. So 1 pound at birth. All right, Kappa started at 2 pounds at birth, so it was a heavier baby. And then to find its rate of change, we've got to be careful because our dots aren't perfect, and even if they were, so if you wanted to go from like this dot to that dot, we got to be careful that it is counting the squares the same as the number. So going from this dot to that dot, we go 1, 2, up 3 squares, but did we really go up 3 units? When we haven't. So from here to here, we went 2, 4, and then, so we got to be careful about the scaling of this one. So our rise goes up 6, and then over 4 squares, but really according to the scale, we only went over 2. So Kappa gained 3 pounds every week. So if we wanted to do some compare and contrast, Kappa started heavier, by 1 pound. But mochi gains weight faster. So that's our comparison. Let's look at another one. So function W and function Z, again, one graph, one table. You want to know which one of these function statements is true. So the slope of W is less than the slope of Z. So before we can even answer any of these questions, let's go find out that information. So for W, looks like I have a point there, 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 there. All I have to do is 2 of them. Up 1 over 2, so the slope is 1 over 2. Our y-intercept is -1. Then for function Z, again, any 2 rows, so I don't have to use these decimal point ones if I don't want to. So from here to here, to here to here, that's 4 and 1, so that's really 1 over 4. And it started, excuse me, at -2. All right, so W is less than Z. That is not true. W is more than Z. 1/2 is greater than 1/4. So we know that's not true. The slope of W is greater than slope of Z. Well, that is true. The y-intercept of W is equal to the y-intercept of Z. Well, that's not true. One's -1, the other's -2, so that's not true. The y-intercept of W is less than the y-intercept of Z. Well, -2 is less than -1, so that is also false. The y value when x is -4 for function W is greater than the y value when x equals -4 for function Z. So we're going to have to compare. So for W, here's -4. Let's use a different color. Let's use purple. So at -4, it spits out -3. I don't have -4 in the table, but I can notice that every one of these rows changes by 2 and 0.5. So if I go backwards to -4, that really changes 0.5, so -3. So are they greater? No. The y value of -4 and both they say is equal. That is true. Again, these last two are a little bit more confusing. I want to take a second just to talk about it again and clear up a lot of this space. There's just a lot going on. All right, so these last 2 check boxes, they want to know when x is -4, what is the y? So according to function Z, they've got this changing by 2 business, and on this side it's changing by 0.5. So using some deductive reasoning here, change by 2, so 0.5, this must have been a -3. Function W, I come over to -4, I go down to the graph because that's where the graph is, and the coordinate would be -4, -3. So they're actually equal. All right, Sonia's revenue versus Jackie's revenue. We've done enough of these tables. I want to see if I have another one. So this is my last example. We're going to do it anyway. Okay. So we want to compare and contrast. So let's start with Sonia's. Find the slope, find the y-intercept. Slope, it's really blurry. Forget what numbers this is supposed to be. So, I believe this is supposed to be a 17. It was just a little too blurry. All right, so it looks like we're changing 6, 6, 6. All the way down, we're just double checking to make sure it's consistent. So this side's consistent, so this side better stay consistent. So that's 24, 24, 24, 24, 24, 24. So it's perfect. Our rate of change is 6 over 24, which must be simplified, cannot leave it like this, to 1 over 4. So we get $1 for every 4 cookies we sell. Our y-intercept is not directly given to us. So I have to kind of do some deductive reasoning. 0. So it changed by 24, which means this side would have to have changed by 6. That means before we started the day, Sonia had $5 in revenue. Maybe that's like carryover from the previous day. Maybe that's, just initial tip that she put into the bucket so everyone thinks that she has some money in there. Whatever it happens to be. She starts off with 5. All right, Jackie's revenue. Again, we want to find M. We want to find B. So B is much simpler. 0, 2. The reason that this graph is dots instead of a whole line, she can't sell parts of cookies. So she can't sell 1.5 cookies, 19 3/4 of a cookie. She just recorded some of the bigger times as well, just 10 cookies in revenue. So from here, again, any dot will work. So I'm going to start with this dot, and we're going to go right to this dot. From 2 up to 5, that's 3. And then even though it's 1 square, that 1 square is worth 10, so it really ran 10. 3/10 is the slope for this one. We could double check with another one if we wanted. We could even go from this dot to that dot because they're both on perfect grids. So from 14 to 20, that's 6. Then 40 to 60, that's 20. 6 over 20 is 3 over 10. Now let's compare and contrast. So Sonia started with more, but Jackie is earning more every day. So 3/10 is 0.3, while 1/4 is 0.25. So Jackie is getting 30 cents a cookie, while Sonia's only getting 25 cents a cookie. But Sonia did start off with more money at the beginning of our exercise.